Thank you. I'm very excited to be here. Okay, so the topic today is expanding expanders, and this is a joint work with Itay Cohen. And let's start with the definition of an expanding expander. And first, let me describe you a problem. So let's say you want to have a network which, well, you want to be well connected, and by well connected, I mean connected as an expander graph. And we all know how to construct expanders, so you simply say you have 10 vertices, you simply connect your graph as a 10-vertex expander, and you're happy. But then you get a new vertex, and you want to add it to your graph. So you know how to construct an expander of size 11, but it may be completely different from the original graph. Okay? What you would have wanted is to simply connect it to your existing graph and not to make too many changes. But usually we think about bounded degrees graph, and you'll have to disconnect the red edges. Can you see the color? Okay, and then you disconnected the red edges, and you can reconnect some of the vertices, but this process stops, and you end up with a graph which is very similar to the previous one, and hopefully still an expander. Okay, so we want to construct such objects, infinite families of expanders which are very similar to each other. And I need to define the similarity between the graphs. So this is simply the size of the symmetric difference between the edges of the graphs. And I want you to participate. So here are some questions. What is the, okay, so the difference, we call it the expansion cost. And what is the expansion cost between these two graphs? Who thinks it's 5? Who thinks it's 8? Yeah, okay, so the answer is 8 because you have 5 new edges and you removed 3 edges. So the answer is 8. And what is the expansion cost between two irregular random graphs on n vertices? Order of? Okay. Almost all the edges will be different. And what is the best we can hope for? So when we add a single vertex, we need to add d edges. So the best we can hope for is order of d. Okay, so there is a previous work by Dinitz, Shapira, and Volodyarsky, which is called Explicit Expanding Expanders. They construct expanders with optimal expansion cost, but they only get edge expansion. Okay? And provably, their construction doesn't give spectral expansion. So our goals for this talk is to prove the existence of spectral expanding expanders, and then to explicitly construct these objects. All right? So let's start with the existence proof. It's simple. So here are the main ideas. So random graphs are with high probability great expanders. And the only thing we need to do is to preserve the random distribution on random graphs, but without replacing the whole graph in each step. And then we can just take the union bound and get their existence. So when I say a random graph, I'm thinking about a union of the uniformly sampled perfect matchings. And let me describe how I preserve the uniform distribution of a matchings with low cost. Okay, so assume you have a matching over 2n vertices, over 8 vertices, and you want to extend it to a larger matching. So I'll describe a process. So you start with the last vertex, number 9, and you choose a uniformly random neighbor. Okay, let's say you pick number 7. Now 7 is connected to 9. You need to disconnect it from number 2, and then connect number 2 to 8. Okay? So the expansion cost, the cost of this process is 3, which is low. And if in the first step you sampled number 8, you simply terminate the process. Okay? And it's easy to prove that if we start with a uniformly random matching over 2 n vertices, this process ends with a uniform uniform matching over 2n plus 2 vertices. Okay? And so we can start with a random graph and then apply this process on each one of the matchings separately, and to obtain a larger graph which is uniformly distributed, and then the union bound just finishes the work. So that's about the existence proof. And now let's talk about the explicit construction. So in the explicit construction, we used the interpolation paradigm, which says you start with a family of spectral expanders, which could be sparse. Okay, you have the number of vertices doubles between each two graphs. And you just interpolate between them. You add new graphs in the middle, so the expansion cost will be small. And how to interpolate between graphs? So in some constructions of expander graphs, there is a natural way for interpolating. For example, in the construction based on the zigzag product, you can describe it as follows. You start with, you have a graph, this hexagon, and now you replace each vertex of the hexagon by a copy of the smaller graph, the triangle. Okay, and the interpolation paradigm says, don't do it all at once, but do it one by one. Each time replace a single vertex with a copy of the triangle. Okay, the same goes in graph lifts. Okay, in a graph lift, you duplicate each vertex, and the interpolation paradigm says that don't duplicate them all at once, but do it one by one. And indeed, our construction is based on graph lifts. And so we start with a graph on the left, and then we lift only vertex A, and then we lift vertex B, and then we lift vertex C. And the vertices, in each step, we have the base vertices, the vertices that come from the original graph, and the already lifted vertices, which come from which live in the world of the graph lift. And I want the base vertices to be connected just like the base graph, and the lifted vertices to be connected just like the lifted graph. And I still need to specify how to connect the vertices in the cut. Okay, so we call it, so we partition the vertices to base vertices and lifted vertices. And we call it, the intermediate graph is called the partial lift, the L partial lift. Okay, so we lifted only the vertices in L. And this is how I connect the vertices in the cut. Okay, so if vertices in the base graph B and L were connected, so now I duplicated the vertex in L, and I connect the vertex B to the two copies of the vertex, the lifted vertex, with a weighted edge of weight 1 over square root 2. Okay? And let me ask you, what happens to the degrees of the vertices? Let's say, what happens to the degree of the vertices in B?
It's a weighted degree.
Yes. The sum of the weight of the edges. So previously, let's say it had an edge between B and L of weight 1, but now we duplicated the vertex L, and it has two edges of weight 1 over square root 2. So the weight increased from 1 to square root 2. Okay, so these partial lifts are no longer regular graphs. Okay, so I need to define spectral expansion for non-regular graphs, and there are, let me skip here, and there are two definitions. So one is the spectral expansion, spectral gap of the adjacency matrix, and the second is the spectral gap of the random walk matrix, which are no longer the same because the graph isn't regular. And this is how the adjacency matrix looks like. So you have the adjacency matrix of the base graph, and you have here the adjacency matrix of the lifted part. And here you duplicated the edges in the cut with a weight, with the appropriate weight. Okay, so I described the constructions, and now here are some important facts about graph lifts, which will allow us to deduce the spectral properties of these partial lifts that I'll describe. Okay, so I guess most of you already know it, but in a graph lift, you have a base graph, and then the lift of the graph is just you duplicate all the vertices, and you connect. So each, let's say, you duplicated A to A1 and A2. These are called the fiber of A, the fiber of a vertex, and you connect two fibers by a perfect matching. Okay, so this is one lift, and this is another lift, and yeah. And the most important fact that allows us to analyze these partial lifts is that we can track the eigenvectors, not only the eigenvalues, but the eigenvectors of lifts. So if we know the eigenvectors of the base graph G, we have a complete characterization of the eigenvectors of the lift of the graph. Okay, so if V was an eigenvector of G, then VV is an eigenvector of the lift of G. And by VV, I mean you assign the same value to the two vertices in the fiber. Okay? And for these eigenvectors, the eigenvalues are preserved. Okay, so all the eigenvalues of the base graph are also eigenvalues of the lifted graph. And the other eigenvalues are of the form V minus V. So in each fiber, you assign each fiber is sum up to 0. And the exact eigenvalue depends on the chosen lift. So we have many lifts for a graph because you can choose different perfect matchings between the fibers. And the last important fact is that we know how to construct, thanks to our work of Bilu and Lineal, we know how to construct families of spectral expanders based on lifts. So each graph is the lift of its previous one. And these graphs have optimal spectral expansion up to logarithmic factors. Okay, so here are our main theorems. So these partial lifts have the same eigenvalues or good expanders as the full lift itself. And this is when you measure the adjacency matrix. And as for their normalized spectral expansion, they are still very good expanders. You only lose a constant factor. Okay, so let's see the proof. So just like in the full lift case, we partition the space to two parts. The one we call the parallel space, which is like we had before VV, which was the eigenvector of G. Now so in the lift of G, a vector of the form VV means that you assign the same value to the vertices in the same fiber. So here you only lifted some of the vertices, so you only demand it there. On the lifted vertices, you have to assign the same value. So this is the VLVL. And F-perp will be the perpendicular subspace, in which each fiber adds up to 0. And it's not easy to verify. It's not hard to verify that these are invariant subspaces. And actually, it behaves very similar to the full lift. So if, just like we had in full lift that V was an eigenvector of G, then VV is an eigenvector of the lift, here we have V is an eigenvector of G, then if you duplicate only the L part and you assign the correct weights, you get an eigenvector of the partial lift with the same eigenvalue. As for the perpendicular space, if you do the matrix multiplication, you see that the eigenvector actually corresponds to a smaller matrix, only the blue part, which is the adjacency matrix of the lifted part. Okay? Only the lifted part. And now, here is the reasoning. So you have an eigenvector. You have an eigenvector of AL bar, the adjacency matrix of the lifted part. This adjacency matrix is a principal submatrix of the matrix of the lift, of the full lift. Okay, and then we use the eigenvalue interlacing theorem, which bounds the eigenvalues of the principal submatrix of AL bar. And it bounds all the eigenvalues but the first one. But since we started with a vector from the perpendicular subspace, we know it cannot correspond to the first eigenvector because of Perron-Frobenius theorem. So this way we managed to bound all the eigenvalues of the partial lift, of the adjacency matrix of the partial lift. And this concludes the first part of the spectral expansion of the adjacency matrix of the partial lift. And what we have left is to talk about the normalized spectral expansion. And this discussion will lead us to an interesting random variable, which I'll describe later. Any questions so far? OK. OK, so in order to talk about the normalized spectral expansion, I'll have to assume that my base graph was deregular. So everything I said so far doesn't assume that the base graph was regular. For the normalized spectral expansion, I'll need to assume that the base graph is regular. And the random walk matrix is just the adjacency matrix times the inverse degree matrix, which is similar to a symmetric matrix, so it has a basis of eigenvectors. And let us talk about the degree matrix. So first of all, the degree is constant on each fiber. Okay? The degree only depends on two properties: in which side you are, whether you are in B or you are in L, and the property we call the internal degree. How many vertices? Let's say I'm a vertex in B. How many edges do I send to B? Okay, so these are constant on fibers, and this means that our partition to the parallel space and to the perpendicular space still holds, and these are still invariant subspaces. Okay, and all the degrees are bounded close to D. Okay, between 1 over square root 2D and square root 2D. And the analysis of the perpendicular subspace for the normalized expansion is very similar because instead of because F perp is an invariant subspace of the degree matrix, we can just replace dpl to the minus 1/2 x by y, and then just repeat the argument from before. Okay, so this is really easy. And the more interesting part is the parallel space. Okay, so for the parallel space, we recall that we assign the same value to vertices in each fiber. And these are linear constraints, and the parallel space actually has dimension n, which is n is the size of the base graph. And so this is actually an n-dimensional problem, even though we work with a partial lift, which can be larger. So using some linear algebra that I skip, we translate the problem from the large dimensional problem to a small dimensional problem. And this could be a little misleading because this looks like a random walk matrix, but this is not. This d to the minus 1 is given by this definition. So you just take the degree in the partial lift of a vertex, and for a vertex in L, you just take a representative. And this is an n by n matrix, but it's not the degree matrix of the graph. Okay, the degree matrix of the base graph is just d on the small d on the diagonal. So it looks like a random walk matrix, but it's not. And let me skip some linear algebra and tell you that during the analysis, we had to bound this quantity, 1 over the degree of the vertex when we sum over only the vertices of the original graph, but we take the degree of the partial lift. Okay? And yeah, okay, so actually maybe I forgot to say something important. Here, when we translate the problem from a large dimensional problem to an n-dimensional problem, the important fact is that we could keep track of the first eigenvector during this process. Okay, since this is a random walk matrix, we know its first eigenvector, but this is not anymore a random walk matrix, and just because of the way we did the translation between the problems, we know how to keep track of the first eigenvector. And so all we have to do in order to bound the other eigenvalues is to bound the Rayleigh quotients of vectors that are perpendicular to the first eigenvector. And okay, so in order to answer this question, we needed to understand the degree in the partial lift, which depend in the internal degree of a vertex V. Okay, so let's say I'm a vertex in B, then my internal degree is the number of edges, number of neighbors I have in the set B. And let me restate this question, so forget about B and L and partial lifts. So we needed to answer the question. So you have a subset S in V, and you have a random variable that samples S in S and returns its internal degree. And what we wanted to know is its expectation and its higher moments. So what can you say about expectation? So its expectation is simply the expander mixing lemma. Okay, or Alon-Chang theorem. And what can you say about higher moments? So this is if you think about a random graph or a random set S, this is the expected distribution of the degree, the internal degree of a vertex, right? We expect it to be somewhat binomial or something. And what we could prove is that in some way, a generalization of the expander mixing lemma to higher moments. So this is what we prove, we just bound the second moment of the expander mixing lemma. And we generalize it to the mth moment of the expander mixing lemma. And this allows us to bound the quantity I showed you before and skipping a lot of linear algebra, proving the result. And also, this generalizes well to lifts of higher order. So instead of duplicating the vertex into two, you have a general notion of k-lift in which you replace a vertex with k vertices, and everything goes just the same, and we have this result for a general k-lift. Okay, so the adjacency matrix stays an expander, independent. I mean, as good as the full lift itself, and there is no dependence in k. And as for the normalized spectral expansion, we get a factor of k. But if we set, so remember we had the square root 2 before, a weighted edge of weight square root 2, 1 over square root 2. So if we choose k equals 4, we get 1 over square root 4, which is 1/2, and then we can just duplicate all the edges and get a graph instead of a weighted graph with parallel edges. Okay, so don't worry about the weights on the edges. It is solved. And I think that's it. Well, I have a question. You should ask, can you get regular graphs this way? I mean, my construction yields non-regular graphs. And the answer is no. This paradigm is limited, and it cannot yield regular expanders. And I think I don't have the time to show you why, but so this paradigm is limited to yield only non-regular graphs. Yes?
Just to follow on that, is it that periodically you get a regular graph when you complete the lift? It's only that, like, in between when you're doing the partial lifts that you have irregular?
Yes, so the partial lifts are not regular, but once in a while you get to a full lift, and then you are back regular.
So they're never that far from
Yes.
regular?
Yes, so the degree is always between 1 over square root kd and square root kd. Thank you.